Greetings and welcome, ladies and gentlemen, boys and girls. It turns out, we've already learned a little bit about this, but it turns out that common logarithms are logarithms that are commonly used. It's not just like rare Pokemon compared to like common ones, but it turns out that log base 10 of something is the same as just log of that something. All right, so a lot of times we work in log base 10, primarily because our whole counting system is base 10, right? Because if I count, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then I restart the cycle, and I'm 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then I restart the cycle because I've got two sets of 10 there, and then if I'm counting like 98, 99, 100, like I've now hit a third digit of sets of 10, right, and everything's base 10. And it turns out we'll also have some benefit working with scientific notation. So the idea here is that if no base is written, if no base, that's a weird space between the I and the F. If no base, it is 10. Right? Or as is commonly quoted, that 10 is the hobbit in the land of logs. Right? It's the invisible implied number in this universe. So that's one thing, I guess, that we can consider. So let's compare and evaluate some of these. Here's an example. So if log of 1.2, here we go, is equal to 0.079 dose-ish. All right, let's find the following. So let's find out what is log of 1200, and let's find out what is log of 0.012. Well, maybe just 0.12. Who knows? Let's start with that. So just like we were doing some manipulation of numbers and such with previous examples, it turns out that knowing this fact, I'm able to then translate it into some other ones. And in this case, what I'm going to do is write these in terms of scientific notation. So 1200 is the same as 1.2 times 10 to the what power? How many decimal places would I have to shift it over? Total of 3, so 10 to the third, right? Or let's kind of do these side by side, I suppose. What about this one here? How would I write that in scientific notation? That would be log of 1.2 times 10 to what? Yeah? -1, because it's shifted one decimal place to the left, would bring us back to that, right? And now that I know some properties of logarithms, also notice that these logs, the bases aren't written, so they're implied to be base 10. 10. Here we go. And the log of a product is the same as the, what? Sum of two logs? So that's the same as log of 1.2 plus log of 10 to the third. This would be the same as log of 1.2 plus, oh, that's a weird plus sign, plus log of 10 to the -1. So, notice that log of 1.2 is 0.0792. And what is log of 10 to the third equal to? If I wanted, I could use the powers property, and I could take that 3 out front. I could write that as 3 times log 10. What's log 10 equal to? 10 to what power is 10? Would be the 1, right? So this is 3 times 1, or 3. How about over here? This would be 0.0792. And then this would be plus what? -1, because I had to use the power property. -1 times log 10. Log 10 is 1. -1 times 1 is -1. And it turns out, what do you notice is similar between these two things? Yeah. It turns out there's a word to describe these two pieces. All right. That decimal portion of our answer. And it is called the Barnacle Boy and Mantissa. No, Man Ray. Mermaid Mantissa. There we go. That's what it's called. The Mantissa.
Mantissa?
Apparently, that's what they call it. And like praying mantis? Ooh, I don't know. I'll have to look up why it's called a Mantissa. And these two components, although they're not the same, right? Those are called the characteristic. All right. I mean, they're the defining characteristic that made each of those unique in this situation, right? So, and it turns out the Mantissa, we usually want to be positive at all times. And we'll see an example in the next situation where it won't be at first, and we'll have to manipulate some stuff in order to make it all work out. Right? So I think you could imagine that if I then wanted to find out what is log of, if I have another 0 there, the Mantissa would be the same, and this would have been a 4, right? Or if I had 3 more zeros, this would just be a 6, and then the Mantissa is the same, all right? Because it'd be 3 plus 3 more, right? So, or if I wanted to shift the decimal in the negative direction even more, we could do that as well. So, let's find the characteristic and the Mantissa of this problem. Find the man and the char for the following. What if I have log of 0.0038? So let's actually just plug this straight into a calculator and then see if we can convert this to mantissiness. So notice that with our calculator, notice that I've got log right here, and when I hit log, oh, I got to turn it on actually there. Yep, there we go. There's some math for you. So when I hit log, it's implied that this base is 10. So I want to figure out what is the log of 0.00. Man, this is very exciting. 38. Suspenseful. And I hit enter, and I get negative 2.42, blah, blah, blah. Right? So negative 2.42, negative 2.4202, blah, blah, blah. Okay?
Do you have to plug it into the calculator?
Well, in this case, yeah, because I wouldn't have that on a chart or anything like that. I mean, we could have written that in scientific notation and maybe found some other interesting things. So, I mean, maybe you'd be tempted to say that the characteristic is the -2 and the Mantissa is the 0.4202. But this is actually kind of a negative. So this is an interesting situation that we'll do here, where it turns out what we can do is add 10 and subtract 10 is what we can do. It's kind of a weird situation. So watch this. I'm going to add 10, which would make this part positive, and then subtract 10 on the outside. All right, so I'm going to hit plus 10 here. And I will get 7.5797, or 8, I guess is the last one. Sorry, my apologies. And if I subtract 10 from that, let's see, minus 10. And now I can kind of separate this out into the 0.5798 plus 7 minus 10, all right, where I'm separating out the decimal part. And what is 7 minus 10 equal to? Plus negative 3. Yeah, so it's kind of a weird-ish thing, but this will be our Mantissa, and our characteristic will be over here.
So you have to do that for each problem. You have to add 10.
Only when we get a negative outcome. But let's actually see. I wonder if I did do this separate way, using scientific notation, we wouldn't have to deal with that. But I mean, you guys agree that adding 10 and subtracting 10 isn't changing the value, it's just changing. I just changed kind of the way things looked, and I rearranged and combined this with a negative 10. Just to make sure that my Mantissa was a positive representation. What if I did do this in the scientific notation method? That would have been the same as log of 3.8 times 10 to the what? How many decimals is that? 1, 2, 3, I think. The way I like counting with for when the exponent is negative cell phonies is we've got 3 decimals if I do include the decimal to the left of the decimal point, and I would get to the negative 3, right? 3 decimals, whether I count it this way, or 3 zeros, whether I count it that way. So this is the same as then log of 3.8 plus log of 10 to the negative 3. And I believe if I do log of 3.8 on my calculator, I get the 0.5798 plus a negative 3. So I could have done it that way as well. But so interesting stuff, perhaps. And the last thing we're going to learn today is the antilog. What? Antilogarithm. So antilogarithm. All right. What would you guess an antilogarithm is? Something that isn't a logarithm. This is somewhat I guess I'm going to describe it this way. It is the inverse of log base 10. Okay? So if I wanted to calculate anti-log of 3, that is asking what is the inverse of log base 10 of 3. Now, what was a logarithmic function the inverse of originally? Of an exponential function. All right, logs were inverses of exponential, so the inverse of a log is just the inverse of the exponential. And kind of like the enemy of my enemy is my friend situation. It turns out this is just the exponential of that. Right? Anti-log, it's implying that this is base 10. So, so the inverse of an inverse is the original exponential that perhaps you would have thought about, and then 10 to the third is 1,000. Okay, so if I wanted to know, actually I think you can take the antilog of, say, -2. That would just be 10 to the -2 equals 1/100, I believe. And actually, just to indicate that antilog is the inverse of logarithms, which is also the same as an exponential, check out on the calculator. Notice, well, actually, you guys don't know sine functions yet, but sine and sine inverse are together. Remember how we used the -1 exponent to find inverse functions back in the day? Like, we had f of -1 of x, f to the -1 meant the inverse of that function. Right, so sine and sine inverse, its secondary function is an inverse. Cosine, cosine inverse, tan, tan inverse. And it turns out log and its inverse is just 10 to the x. Okay, so if you want to calculate the antilog of something, all right, what you would do is you just hit second and log button, and it just it doesn't write antilog, it just writes it as 10 to the what? So antilog of 3 is just 1,000. All right, so I just want to point out antilog is the inverse of an inverse, so it's the exponential function. It's kind of like doubly inversed, right? I always like to think about the enemy of my enemy as my friend situation, somewhat. So anyways, so that's pretty much it. Common logarithms sounds like a common law marriage. What's the rule for that? What if you live with someone 7 years or something, then you're recognized? 10? Okay, I didn't know what the dealio was. I've never done that, so I wouldn't know. But common logarithms and anti-logarithms is what we covered today. Base 10, bam. It would be entirely different if we all had 12 fingers. Just, we'd probably work in a base 12 number system instead, which would be weird. If you're interested in a base 2 number system, those already exist. That's binary, where it's either, ones or zeros, on or off, situation like that. Well, anyways, goodbye, internet friends. Goodbye.